On the morning of February 1st, 2003, the Space Shuttle Columbia was re-entering the Earth's atmosphere after a very successful 17-day science mission when ground control personnel received unexpected high-temperature readings from the shuttle's left wing and wheel well. A few minutes later, NASA lost all contact with Columbia. A catastrophic event had occurred, resulting in the loss of Columbia and her 7-member crew.
We find the best among us, send them forth into unmapped darkness, and pray they will return. They go in peace for all mankind, and all mankind is in their debt.
Determining the root cause of the Shuttle Columbia breakup was a monumental task that began with the search of the 2,000 square mile accident debris field in East Texas. More than 25,000 people from 270 organizations helped to recover 84,000 individual pieces of orbiter debris and lay them out in a large hangar. A nationwide mobilization of all NASA centers, the armed forces, other government research laboratories, and many of the country's aerospace contractors was tasked with helping to find the cause of the accident, analyzing the phenomena involved, and developing solutions. Using new analytical technology not available when the space shuttle first flew, NASA investigators also re-examined shuttle systems to ensure the shuttle's return to flight will be as safe as modern science and technology can make it. NASA Glenn Research Center personnel initially focused their expertise on two areas: an examination of the reinforced carbon-carbon, or RCC, panels along shuttle wing leading edges, and ballistics testing and analysis of foam impacts. After reviewing video of the launch, investigators thought one of the events that was not well understood but may have played a role in the Columbia accident was a foam strike. At 81.9 seconds after launch, a piece of handcrafted foam weighing just over 1.5 pounds detached from the external tank and struck the leading edge of the Space Shuttle Columbia's left wing, the area of the unexpected high temperature data. The teams of NASA experts sent to assist the investigation posed several questions. Where did the foam seen on the launch video come from? Had a breach occurred in the RCC panels that protect the shuttle from the extreme heat of atmospheric re-entry? If so, how were they breached? Could the recorded foam impact have been responsible? If it was, had the cumulative heat effects of multiple missions weakened the panels, or did they fail because the force of the foam impact was hard? Finding answers began by assembling the RCC panel debris into a three-dimensional reconstruction of Columbia's left wing leading edge. Reinforced carbon-carbon is strong but brittle quarter-inch thick material that actually grows stronger when exposed to high temperatures. Interwoven carbon composite layers are sandwiched between two silicon carbide layers. Because carbon oxidizes when exposed to air, cracks from the manufacturing process in the outer silicon carbide layer are sealed with glass. Experts from several NASA centers studied the debris from the leading edge panels. Glenn personnel undertook the chemical characterization of the slag, the molten deposits on the inside of the panels. A variety of non-destructive evaluation techniques, including visual observation, X-ray imaging, thermography, and ultrasound, were used to examine the panels before cutting samples for further analysis. Glenn metallographers prepared the RCC and slag samples using a unique process. The RCC was cross-sectioned, then vacuum and high-pressure impregnated with fluorescent epoxy to preserve internal structures, and polished to reveal the microstructure. NASA Glenn's Electron Microprobe facility analyzed the chemistry of the RCC samples with a wavelength dispersive spectrometer. The sample's atomic microstructure was analyzed in the Field Emission Scanning Electron Microscope facility. These tests supported the agency-wide hypothesis that the breach had occurred in RCC panel 8L and determined the order of events during the breach. Rivulets of molten insulation meant the temperature of the superheated air flowing through the breach was in excess of 1,649 degrees centigrade, enough to melt all leading-edge materials except RCC. Though the launch video seemed to implicate the foam strike near panel 8L as the cause of the breach, at the time of the Columbia accident, it was unknown whether or not a foam impact could break an RCC panel. To find out, NASA began ballistic impact tests while the RCC panel was still being investigated. NASA Glenn Ballistics impact researchers constructed a unique gas gun for small-scale ballistic testing of external tank foam impacting RCC. The gun barrel was mounted to a vacuum chamber, a critical capability enabling impact tests at low pressure, low temperature conditions similar to those during the Columbia foam strike. The small-scale tests proved a foam strike could indeed break the RCC material. The ballistics impact facility was modified to run tests to support full-scale testing of an actual RCC panel 8L with similar flight history. NASA Glenn personnel joined other NASA experts at the Southwest Research Institute near San Antonio, Texas, where the full-scale impact tests were conducted. NASA Glenn provided extensive photographic instrumentation and data acquisition equipment, as well as analysis expertise for the tests. When the angles, speed, and size of the foam projectile were set to simulate conditions during the Columbia launch,
5, 4, 3, 2, 1, 0.
the impact created a hole 16 by 17 inches in RCC panel 8L, confirming findings of other investigation teams that the foam strike led to the Columbia accident.